Yoshi, are you ready?
Yeah.
Okay. So good morning, American colleagues. Good afternoon, our European colleagues, and good evening to our Asian colleagues. And welcome you again to this World River and Delta System, the Source to Sink webinar series. And today is 22 of this year. We have 35 webinars already in 2020, but starting this year now is the number 22. So today we are very happy to invite Professor Yoshi Saito from Japan and Shimane University come here talk about the holocene delta evolution response to the sea level changes and the coastal setting lessons we learned from Asian deltas. So before I introduce Yoshi, and I want to mention Wei Jun from University of Delaware. This coming Friday, we'll talk about the carbon cycle and in particularly the cycle and the fluxes in the world large river impact ocean margin, the river dominated ocean margin, and the inorganic part. So please mark your calendar. I guess the region also will cover at least the Mississippi River and Yangtze River and other river system he has been working on. So Yoshi is a professor and a director of the S2S Research Center, Shimane University, Japan, since 2017. And before that, he's a senior scientist in Geological Survey of Japan in Scuba. He received a bachelor degree geology and mineralogy from Kyoto University and a doctor from Kyushu University. And so he had been working on the geological survey for almost 38 years. Yes. And he has focused on mainly sedimentary process in the coastal zone to the shelf. Particularly in the last 30 years, he has conducted field survey in the Asia river delta system, like the delta in China, Vietnam, Cambodia, Thailand, India, and other Asia countries. And he was one of the co-leader of the IGCP of a 475 project. I think working with our friend of Steve Goodbread and Zhong Yuan Chen. And he received a champion medal of Vietnam Academy of Science and Technology, and also Distinguished Contribution Award from International Congress of Asian Marine Geology. And he has more than 300 peer-reviewed publications. And this is really amazing. I guess he may also introduce a little by himself. I want to say Yoshi really a godfather of Asia river delta studies, particularly in the last 30 years. For example, he initiated collaboration over the Yangtze River Delta in 1992, 97 of the Yangtze, the Yellow River, this is Yangtze, then coming to the Mekong River Delta, and also Chafia River, the Red River, and also most recent 7 years, he has been working on Indian Godavari and Kyushu deltas. So that's really amazing work. And Yoshi personally is also my mentor. He's my PhD committee member. I remember when I was a graduate PhD student first year, I stopped in Japan. I went to his office. He bring 2 piles of the reference for me to use. That I make a lot of copy. That's the really a starting point for me to interest in that kind of Asian river system. As you know, follow his step. We also study the feet of those rivers after they deliver to the estuary and the delta on the shelf. So I think it is a great mentor, great colleague, and great friend. Thank you, Yoshi. And as we point out, he published more than 300 papers. If you look at his citation, is sharply increasing every year. Now is 2,000 citations every year. Now it's almost, maybe today is already more than 20,000. So I'm pretty sure before he retired, he maybe shoot up to 30,000. So Yoshi, and so I think now is your turn. Please share your screen for the presentation mode. Great.
Yeah, thank you very much for the poll. So
yeah, looks good.
it's okay?
Yes.
Yeah. So thank you very much. So it's my great pleasure to have the talk here. Yeah, Paul asked me to have the presentation last year, but I decided to have the talk a little later. It was very good for me because time zone is so late in Japan. So now it's okay, it's at 10 p.m. But 2 weeks ago, it was 11 p.m. It's so late for me. So today, my talk is based on my research last 30 years. And I focus on the recent progress on the delta research. Particularly focus on the holocene. So Asian delta's characteristics and the recent knowledge of the sea level history and the response of the sea level change to deltas. And today, my talk focus on the holocene, but only 3 to 9 Ka, not human impacts, not modern systems. So deltas is, as you know, it's a term delta was first applied by Herodotus in his book, Histories, about 450 years BC. It's a triangular alluvial deposit at the mouth of the Nile River. It's a deltas is a term. It's called by Ionian people, Greek peoples, at the mouth of the Nile. I like the definition of this Elliot definitions I took later. So deltas is a triangular shape of the Nile, but originally this term comes from just only the river mouth bar, triangular shape. So first description, the definition of deltas, maybe the Charles Lyell's textbook's Principles of the Geology. In the first edition, already there are some delta chapters. And the fifth edition's 1837, it's a glossary of the terms. There is the deltas. So if you look here, so at that time, delta is originally is a river mouth bar. This is a fifth edition of the Principles of Geology. And the ninth edition already map of the Ganges Brahmaputra in his book. So maybe this is a first description and the map of the deltas in the textbook. The famous diagram is a Galloway diagram as a 1975, is a ternary plot, the rivers and the waves and the tide. Basically, this is a morphology or subaerial morphology to identify the delta factors. And before that, there are some description on the deltas. For example, in the Fisher shows the constructive deltas or the destructive deltas. So that is created the river deltas in the constructive, and the waves and tides, the rework, the sediments, that is destructive deltas. And in 1992, Darimper and Boyd, they shows another definition on deltas. This is a coastal depositional systems in the context of the sequence stratigraphy. So basically the coastal systems, all coastal systems divided two parts, transgressive or regressive, because the sequence stratigraphy is an interpretation related to the sea level changes. So transgressive, that means the shoreline migration, the landward. The regression is the shoreline migration seaward. So this is a delta system, but also here are the deltas. It's a Estuarine delta or bayhead deltas. So basically, delta is a typical regressive depositional system at the river mouth. So there are mainly the two factors controlling the shoreline migration. One is rate of sediment supply, another one is the sea level changes. So two factors mainly control shoreline changes. So shoreline migration landward at the river mouth is just estuary, and the shoreline migration seaward we call deltas. There are some definitions deltas after the Elliot's. Also, this is the Don Wright definition, and also the Janak Bhattacharya's definition. Anyhow, delta is a depositional body or morphology, and fundamentally regressive in nature. So deltas in Asia. Already there are some talks refer to this paper, the Milliman's book. And the water in Asia, only 30% contribution in the global, but sediments roughly is 70%. Huge sediments supplied from Asia to the coast. But 70%, if we look at the Borneo Islands, that's 910 million tons of sediment supplied from only one island. That's much more bigger than Yangtze and Reds, Mekong, Chao Phraya total. So 70%, but half of them is a tropical island, Taiwan, Sumatra, Java, Borneo, Celebes, Timor, New Guinea islands, the other large rivers. So we must be careful. So 70%, but half is come from the small island. But today I focus on the large river deltas. So Asian large rivers mostly initiated from the Tibetan Plateau or Himalayas. Flow east and flow south and flow west, making the huge deltas. Delta part is colored in green. So if you look at the relations in delta area and their drainage areas, so Asian deltas plots relatively they have their large delta areas in compare with the drainage areas. So there are some reasons. One reason is the sediment yield in the drainage basins. So Asian delta also has a high sediment yield in the drainage basin. Yeah, so this is because of the uplifting steep high mountains, the Himalaya and the Tibetan Plateau. And also this is a famous area, the monsoon climates, very high precipitations. So both supplies so much sediment to the coast. Another important factor is a stable sea level. So I talk later, these parts surrounding glacial areas, North America and the European regions, sea level is continuously rising during the Holocene. But the far field, we call far field areas, Asian regions, highest sea level is about 6,000 years ago. Since then, sea level is falling. So that's a stable sea level, making deltas, wide delta plains. So that's the two reasons. Main reason is a stable sea level and high sediment yield and discharge make the huge deltas in Asia. So if the sediment supply is constant, So river mouth systems, how to change the estuary to deltas. Mainly it's controlled by the sea level. This is so famous paper, the Stanley and Wong, 1994, in Science. Oops. So they reviewed the 36 deltas in the world. And the base of the deltas, there is a devisal peat and rocks. He compared these data. So that the most of the deltas initiated about 7,000 to 8,000 years ago in a C14 ages. Just before the 1989, Fairbanks shows a continuous sea level records from the last glacier to the present. This is the first sea level records based on the coral. This sea level records shows a very rapid sea level rise, followed by the slow rise in sea level. Boundary is about 8 Ka. That's coincide with the delta initiations. So most of the deltas initiated that caused by these changes of sea level. After such studies from 2007, there are some papers show more detailed sea level records. This is a Michel Bard papers published in ECSS 2007. He shows the sea level records based on the basal peat in Singapore. Very rapid sea level rise before the 8, around 8 to 9 Ka, followed by the further sea level rise. And also the Mark Hijim and Kim Cohen also show the rapid sea level rise around 8.5 Ka, maybe correlated with the Lake Agassiz collapse in North America. And Hori and Saito, myself, and they also published a paper, 2007, based on core data, the Yanzi, Red, and the Kiso, Japan. They show the all estuarine system give up around 9 to 8.4 Ka. That means a very rapid sea level rise occurs at that time. Most of sea level records is reliable sea level record is a coral based on the coral data, but there is no coral data around 8 to 9 Ka in the world even now. The famous areas, the coral from peninsula, also there is a gap here. Based on these studies, the Smith et al. Reviews the sea level change, early Holocene sea level rise. They show the very rapid sea level rise between 8 to 9 Ka. This figure shows the coral data. Most of coral data using Politis or something, very shallow species, less than 5 meter deep, living depths, but only this interval, deep water species. There is no coral, good coral data in this period. So this is early Holocene sea level rise jump. After that, the Yuan Zhangfa shows a sea level change, sea level curve from the Yanzi. They show the very rapid sea level rise from 8.5 to 8.2 Ka, close to the 3 centimeter per year, followed by the further sea level rise. And Changiri et al. 2014 also shows a rapid sea level rise around the data, in and around the data of the Mekong. So very, very constant sea level rise through the early holocene, but rapidly jump between 8 to 9 Ka. So what happened at that time? So that is a famous Lake Agassiz, North America. Lakes collapse at that time. So Laurentide ice sheet collapse and Lake Agassiz waters flow directly into the Hudson Bay. That is 8.47 Ka. But that water is only explain 40 to 50 centimeters sea level rise. But this is famous for the 8.2 Ka cooling event. And also another paper shows the Lake Agassiz collapse, and also the not only Agassiz collapse, also the surrounding iceberg also collapse together. So Lake Agassiz collapse and iceberg collapse and also surrounding melting of the ice make the huge sea level rise at that time. So formally, this is roughly the very roughly rapid sea level rise followed by the slow sea level rise around 8 Ka. This is a C14As. So now we know 8.2 to 8.8, very rapid sea level rise occurs. It's a calibrated age. And most of deltas initiated after this rapid sea level rise. So the Mekong is initiated, initiation is about 8.1 to 8.2 Ka. The Yangtze also 8.0. Japanese rivers are river 8, Naka river 7 to 6. And the Yellow and the Godavari, Krishna a little later. I talk later. So delta initiation, inceptions, is just after this sea level jump. This is a very important boundary to understand the Holocene delta in the world. After this sea level jump, still there is a glaciers in North Laurentide ice sheet. There are 2 glaciers, all glaciers melting until the 6.5 Ka, contribute about 5 meters further sea level rise. This is a Laurentide ice sheet areas. This is rapid sea level rise, and this is a further sea level rise about 5 meters, contribute 5 meters. This record is sea level rise, it recorded in Swedish Baltic Sea, and also the Singapore, and also the Yangtze and the Mekong and the Godavari Krishna and the Guillemot River, Korea also. 8 to the 6.5 Ka, sea level rose about 5 meters. Okay, how's the response of deltas, these changes? So this is a Mekong examples. This is a timeline 10 Ka to 4 Ka. So until the 8 Ka, estuarine sediments are gradationally stacking here, but the delta progradation starting 8 to 7, and the more progradations, rapid progradations after the 4 Ka. This is D sections. This is AB sections close to the inside the valleys. Also shows 11, 10, 9, and 8 is a more gradational stacking of estuarine sediments, followed by a little gradation and progradation both, and after the 6 Ka, progradation dominant stacking patterns. And the maximum flattening surface of the Mekong this is a nice records based on the pollen analysis that it identifies a mangrove species, identifies the details in the tidal zone. So this is a transgression and the regressions based on the mangrove species. So that is 8.1 to 8.2. It's a maximum flooding surface of the Mekong. After the maximum flooding surface, marine mangroves distributions expanded landward related to the rise of sea level. So shorelines migrate seaward, but the marine inundations expand also the landward. So this is a summary of the Mekong. Maximum flooding surface 8 to 8.2 Ka. Before that is basically the estuarine phases, and followed by the progradational or aggradational stacking pattern and the delta system. The marine inundation expanded landward also, and then followed by more rapid progradations. Okay, after the 7 Ka, sea level still rising. Presently is the highest sea level during the holocene. This is 3 model of the sea level curve. 6,000 years ago, it's about -3 meters globally. We must think about the 2 factors to understand the local sea level changes. One is glacial isostasy, another one is hydroisostasy. After the melting of the glaciers, this part is uplifted, and the surrounding areas, due to the volcanic collapse, this is subsiding. This is a near field of the glaciers. The Asian countries, we call the far field. There is no impact on the glacier, but so much impact by the water loading. We call the hydroisostasy. Margin of the continent is uplifted, the ocean floor is subsided. So this is tilting as a leveling effect. So if you look at the global sea level curve during the holocene, these subsiding areas around the North America, European regions, so sea level is continuously rising. But in far fields, Asian countries, sea level is we showed about 6,000 years ago, 2 meter high, and then sea level is falling. So this rising sea level areas, most of the coastal morphology is estuary and the barrier islands. So east coast of the US and the Baltic Sea, Wadden Sea, there are so many barrier island estuaries in these areas. But most of Asia is a far field. So sea level is stable or falling, so deltas and strand plain developed well. So this is a notch. Notch is a wave erosions, we call the bioerosions at the middle sea level, middle mean sea level. So this is come from this data is from the Mekong. This now is a 2 meter above the present sea level. But globally, 6,000 years ago, sea level was -3 meters. That means this part is uplifted 5 meters for the last 6,000 years. This is hydroisostasy. This is another example of the notches here is near the Red River deltas, about 2 to 3 meters high 4 to 6,000 years ago, then sea level is falling. This is also the hydroisostasy effect. This is uplifted by such effect. So this is some data on the spatial distribution of the tidal isostasy effect. So basically, inland is much more higher and down to the ocean. So it's something like a tilting. So even the one deltas, uplifting rate is different. Inland is much high and the coastal zone is low. So this relative sea level change, we must think about in the delta evolutions, particularly in Asia. So this is an example of the Red River. Relatively sea level is stable in the middle Holocene and falling. So how to respond to the deltas? These are Red River examples. 7 to 6 Ka. So after the delta initiation, about 8 Ka, so delta progressed here, and the coastal areas occupied by the mangrove sediments. However, after the falling the sea level, all these parts are abandoned. They change to the holocene marine terraces. So you look at the vertical section here, the timeline 10, 8, 6 Ka, a gradational stacking in this area, mangrove areas, up to the 4.5 Ka, then abandoned. This is a Mekong example. Mekong also the marginal areas, mangrove and the intertidal flats, gradations until the 4.5 Ka, then abandoned, change to the fluvial environment. This is another example of the Yangtze. Yangtze deltas prograded more than 250 kilometers from this area to the present. If we look carefully, the initial stage of the Yangtze, this river mouth bar, old river mouth bar is a little high. This present rivers cutting this river mouth bar, old river mouth bar with a 2-meter high scarp. If you look at the core, this is taken from the this Holocene terraces. A gradational stacking also until the 4 Ka, then abandoned. So most of deltas initiated after the rapid sea level rise, so about 8.2 Ka. Before that, shorelines migrate landwards. Most of the depot center was a coastal zone and intertidal zone estuaries. After the regression, slow rise of sea level, gradation and progression both occurs until the 6.5 Ka mostly. Then, more relatively stable sea level, delta prograde more rapidly to the seaward. Another important factor is in Asia, until 4 Ka, the aggradation occurs. That means the rate of the uplift is less than the rate of the sea level rise. However, after the 4 Ka, most of such coastal plain is abundant, changed to the Holocene terrace, the incision starting. Then enhanced delta progradation occur since 4 Ka. Okay, that is a roughly outline of the Asian delta evolutions. The another part is a wave-dominated coast. So I now show the Mekong, Songhong, and the Yangtze. Most of deltas located in the inside the valleys. But other deltas, Godavari, Krishna, and Yellow, both coastal settings are more wave dominated, a completely different setting. So this is the Godavari deltas. See, this is Godavari deltas. Most of deltas I mentioned before, Yangtze and Mekong and Red Rivers, most of delta plain consisting of the marine sediments. However, this Godavari and Krishna deltas are a little different. Apex is located here. And this is alveolar fan or alveolar plains. There is no marine sediment here. The marine sediments only distribute the marginal parts. The main characterize the beach ridge plains. This is a delta evolution. It's a first delta lobe was here, and the secondary delta lobe, the third delta lobe, shifting like this. So this is wave dominated coast. So most of the A delta, number one deltas truncated by waves. Number 4, also this part is truncated by waves. If you look at the cross sections, most of delta sediments just only monotonous progradations. There is no transgressive systems, and there is no sediment before 6 Ka. This is Krishna deltas. Also, they are same. The apex here, this is alveolar plain, mostly is alveolar fan. Delta is only this part. It's a little complicated structure of deltas, but if you look at the cross sections, the basically the same, monotonous progradations. There is no sediment before 6 Ka. So perturbation potential of transgress before the 6 Ka is very low because of the surface erosions. So only the regressive delta system developed in this wave-dominated setting. So this is the final figure of my talk. So holocene evolutions of the delta. So basically, most of delta's development is controlled by the sea level changes. So very rapid sea level rise between 8.8 to 8.2 Ka. This is, other times, it was estuary. After stable sea level, slow rise of sea level, 8.2, most of deltas initiated. The time of the initiation, it depends on the sediment supply. And the coastal on-lap aggradational stackings occurs related to the sea level rise. And the coastal on-lap aggradations recognized until 4 Ka. And the enhanced delta progradations just only the last 4,000 years. And this main boundary, 4,000 and 8.2, is coincide with the holocene divisions. This early to middle holocene divided by 8.2. So this is very important boundary also in a delta understanding. And also 4.2 is a boundary of the middle to late holocene. It's a very, very famous cooling events. Most of civilizations collapse at that time. And I show the sea level changes, sea level curves, 4,000 to 6,000 years, sea level relatively stable, and then falling. That's maybe related to the cooling events. So since then, delta progradations enhance. So thank you very much. So I had so many colleagues study colleagues in these countries. This is a summary of all my research. So thank you very much.
Well, Yoshi, what I can see is amazing. Thank you so much. And you give so far the shortest talk, only 35 minutes. But this is the best talk, one of the best. And also the best talk about holocene sea level and the delta evolution. And this is a textbook. I'm so happy we got you and we archive this presentation. I'm pretty sure this will be replayed and watched by graduate student and any people study the sea level and the delta evolution. That is fantastic. This is so far the best, talk about the holocene sea level and the delta evolution. Thank you again very much. Okay, and so as we said, we have plenty of time, have a discussion. This is wonderful. So if you have any question now, you can unmute yourself. You can directly ask Yoshi, or if you like, you can type your question in the chat room, either way. And for those who are watching through YouTube, I know a bunch of people watching through the YouTube. If you have a question, you also can type on the YouTube chat room. I tried my best to read your question. And so, okay, go ahead. So anybody, you can unmute yourself and ask directly.
Well, okay, can I start then? It's
Sure.
Robert Nichols.
Sure.
Yoshi, I really enjoyed the talk. And I'm going to take you in my question to a place you said you weren't going to talk about, which is the future. But I'm just curious, in terms of the world as we have today, obviously is very human influenced. So river discharges being modified, etc. And we have billions of people living in Asia. But if we scrub that, if we just assume that these deltas were evolving without human interference, and we were expecting the rise in sea level that we are expecting now due to climate change. So this is a thought experiment. It's not going to happen. But I'm just curious as to what you would interpret as what amount of sea level rise would really make these natural systems change state back towards something that we saw earlier in the Holocene or in the Pleistocene. Does that make sense?
The early Holocene, most of sea levels, marine areas come into the inside the valleys. At that time, there is no deltas, no wide coastal plains. And it's a completely different setting. Yeah.
But would you, I suppose I'm trying to just ask the question, is there a particular rate of sea level rise based on this geological analog that you would say I would expect to start to see massive retreat of these systems, forgetting all the human interference, which makes things much more complex?
Yeah. If we look at the geological records, rate of the sea level rise is so fast in compare with even the future. And the early Holocene sea level rise is at 2 centimeters per year. And the 8.6, that means 1,000 or 2,000 sea level rose 5 meters. And that is a comparative with the future. Yeah, and the after that, sea level rise is very little, just only 2 meters for 6,000 years, something. Mostly this comes from the melting of the Antarctica.
Okay.
Yeah, and so, yeah.
Okay.
Thank you.
So Tom, go ahead. So
Yes.
if you have a question, you also can raise your hand virtually, then we can know who is the, Tom, go ahead.
Yes, Professor Saito, thank you very much. I have a question. This is not my area of expertise in terms of geomorphology, but when you think of a lot of the marshes that are associated with these deltas with current sea level rise, you're saying, am I correct in understanding that this sort of hydro isostasy, because it's much less in terms of the magnitude of sea level rise in that you described in the past, because it's much lower, the rate of sea level rise, the hydro isostasy is not as much of an issue in terms of marshes keeping pace with accretion?
Okay, and the hydrolysis, it depends on the region. So impact of the hydrolysis is here and here and here is completely different.
Mm.
And maybe along the coast, it's negligible. 2 orders of magnitude or less than the global sea level rise at present. It's negligible. But if we think the delta evolution on a millennial scale, we must think about such a uplifting. So in a shorter time scale, it's not necessary to think such effect.
Okay, yeah, I was asked, okay, that answers my question. I was particularly focused on the mangroves and the marshes and their accretion rates in response to sea level rise. But it sounds like what you're saying is that the hydroisostasy is not so relevant with that.
No.
Thank you very much.
Yeah.
Okay.
And if you look at the mangrove peat or something, at present, the Mekong just only the thickness is at 20 centimeter or something.
Okay.
Yeah, and this regressive system deltas, mangrove sediment is not so much. But most of the such a thick mangrove sediments is like this. During the rise of sea level in the incised valleys, there are several meter thick mangrove sediments.
Okay, so I saw Yap and Michael. Michael, you have a question or I?
Yeah, a comment. Yeah, it's good to see people starting to worry more about the GIA and the hydroisostasy. And I'd say another thing that some people are beginning to look at is also the sediment isostasy, that the weight of the sediment also produces a similar uplift and subsidence around the depositions, and whether or not that might also influence the height of your wave cut terraces.
Pardon?
Yeah.
Okay. Yap.
Yes, thank you, Yoshi. This was a really fascinating talk. I was struck by your last slide where you summarize it nicely, where you say that the wave-dominated deltas initiated much later than some of the other big Asian megadeltas. And I was wondering if you think there's also an effect of delta size, where bigger deltas have initiated before some of the smaller deltas that are either river or tide or wave dominated.
Yeah, because most of the large river deltas has a large incised valleys, and so there are some good spaces for the deltas. But if we look at the Mekong, sorry, where's Mekong? Yeah, even the Mekong, maybe it's hard to prograde more because here is around here is a headland, most of progradation protect. And now, before that, the Mekong is prograded fastly because here is a headland. Now it's receiving the more wave directly to the river mouth. The most of the sediment transported along shore. And it's very hard to form the large river deltas, even small mouths and everything. Most of the deltas, sediment deposits, protected by the headland mostly. Very rare case. If sediment supplies are huge, make deltas, but very, very limited. Not all, yeah. And the small river mouth estuaries, maybe that can make the deltas in such only the estuary, cannot go out.
Mm-hmm. But so it might take a lot longer for them to reach that stage because they're so much smaller and have less river sediment supply.
Yeah, yeah.
Okay, thank you.
That's very interesting. This is also true for the Yangtze and the Irrawaddy. Many of those Asia large delta somehow reach the equilibrium, and even there's some sediment coming down, but the open ocean environment keep it very hard to prograde. But Yoshi, I have a question about hydroisostasis, as Tom mentioned. So the effect of those hydroisostasis in Asia River Delta region, is this the effect is still going on, or is gradually fade away, dying down? This is the first question. Do we have an idea, the current hydrostasis impact still, how much still going on that impact us? And
yeah, there is one paper shows the hydroisostatic impacts on the decadal or 100-year. Just only the 0.03 millimeter, very, very small.
Very, very small now. Okay,
yeah,
good
yeah.
to know. Because in North America, they have the GPS installed across all the North America. They know that every year the uplifting, the rebounding rate, and also the margin, the subsiding rate. But in Asia, looks like we don't have such big scale, data to help us to understand that.
Yeah, and glacial isostasis is much bigger. Hydroisostasis is maybe the 2 order of magnitude is lower.
Okay, second question related. You mentioned because the Asia, most of the delta area sea level fall because the hydrostatic uplifting, this cause sea level relative fall. But do you agree? Is there any middle holocene optimum, the middle holocene warming period? So the climate also a driving factor to cause sea level fall?
No. It's completely different. Sea level is continuously rising, but the rate of a little different. There are still some arguments on the sea level rise.
Yeah, but remember North America, all the way from Miami to Florida, overall in the last 10,000 years is keep subsiding every 2 millimeters per year. 2 millimeters per year. So this is why the east coast of US, they observed the continuous sea level rising event because the land is sinking. And Canada portion is rising, but the margin of east coast is keep sinking, subsiding. That's the reason east coast of US, they observed the sea level rising, but doesn't mean the global sea level is rising.
Yeah, that's so these areas, so surrounding areas of the glaciers, sea level rise is a 2 factors. One is a global sea level rise, another one is a glacial isostasis. So much more than the average US coast.
Okay. Okay. So let's see, we can discuss more this. Anybody have any question? So today we have a little bit more time.
Yeah, it's very interesting, the difference between, I hadn't realized of how much North America is in the not quite the near field, but that middle field where you're seeing the continuous sea level rise because of the collapse of the forebulge, versus Asian deltas seeing that peak. I'd also like to say that Rhodes Fairbridge made me promise many years ago that I would always spell isostasy with an S at the end, not a C.
Interesting. But after the correction of the east coast of US, actually they show the middle holocene also have a high sea level record, because the observed one show looks like keep rising, but after they corrected the subsiding rate, looks like 6,000 or 7,000 years, also should have a high sea level. But I don't know. I mean, it's a complex issue.
I know right now, along the East Coast, it's subsiding, and it's subsiding a little bit faster off New Jersey, as where the peak of the forebulge was.
Interesting. Well, now I think we have a much better understanding than 10 years ago or 20 years ago. When I was a graduate student, when we do this, we do not completely understand, but great. Anybody else? And if not, I would like to mention, this, this coming Friday, Wei Juncai from Delaware University come here, talk about also river dominated ocean margin, the carbon, the PCO2, how much the CO2 released to the air, bring down by those river dominated plume. Okay, so please mark your calendar, come back this Friday. Otherwise, thank you, Yoshi, very much. I know it's 11 p.m. now. So thank you so much. Thank you, everybody, Michael, Tom, and so many friends, Jim Best, Yap, Stu Kyo also around. Thank you so much. And I see you this week and next week. Okay.
Yeah.
Okay, so long.
What's your background?
Yoshi, what's your background?
Which river?
My background, geology?
No, behind you. Your background.
Okay. That's a Mekong.
Typhoon flooding, right?
Mekong in flood seasons.
Oh, Mekong.
Yeah, in Cambodia.
Oh, okay. Great. Oh, it's amazing. Okay, cool. Couple years ago, when the typhoon made a landfall in Tokyo, also have that kind of similar flooding in the river. Okay, cool. Thank you, Yoshi. Okay.
Yeah.
Okay, I need here. Okay.